Hello and welcome to my channel, Learn with Veer. This is Akashveer. I'm reading A Brief History of Time, Chapter number 8, The Origin and Fate of the Universe. This is part. The day after I got back from Moscow, I set out for Philadelphia, where I was due to receive a medal from the Franklin Institute. My secretary, Judy Feller, had used her not inconsiderable charm to persuade British Airways to give herself and me free seats on a Concorde as a publicity venture. However, I was held up on my way to the airport by heavy rain and I missed that plane. Nevertheless, I got to Philadelphia in the end and received my medal. I was then asked to give a seminar on the Inflationary Universe at Drexel University in Philadelphia. I gave the same seminar about the problems of the inflationary universe, just as in Moscow. A very similar idea to Linde's was put forth independently a few months later by Paul Steinhardt and Andrews Albrecht of the University of Pennsylvania. They are now given joint credit with Linde's for what is called the new inflationary model, based on the idea of a slow breaking of symmetry. The old inflationary model was Goode's original suggestion of fast symmetry breaking with the formation of bubbles. The new inflationary model was a good attempt to explain why the universe is the way it is. However, I and several other people showed that, at least in its original form, it predicted much greater variations in the temperature of the microwave background radiation than are observed. Later work has also cast doubt on whether there could be a phase transition in the very early universe of the kind required. In my personal opinion, the new inflationary model is now dead as a scientific theory, although a lot of people do not seem to have heard of its demise and are still writing papers as if it were viable. A better model, called the chaotic inflationary model, was put forward by Linde in 1983. In this, there is no phase transition or supercooling. Instead, there is a spin-zero field, which, because of quantum fluctuations, would have large values in some regions of the early universe. The energy of the field in those regions would behave like a cosmological constant. It would have a repulsive gravitational effect and thus make those regions expand in an inflationary manner. As they expanded, the energy of the field in them would slowly decrease until the inflationary expansion changed to an expansion like that in the hot Big Bang model. One of these regions would become what we now see as the observable universe. This model has all the advantages of the earlier inflationary model, but it does not depend on a dubious phase transition, and it can moreover give a reasonable size for the fluctuations in the temperature of the microwave background that agrees with observation. This work on inflationary models showed that the present state of the universe could have arisen from quite a large number of different initial configurations. This is important because it shows that the initial state of the part of the universe that was inhabit did not have to be chosen with the great care. So, we may, if we wish, use the weak Anthropic Principle to explain why the universe looked the way it does now. It cannot be the case, however, that every initial configuration would have led to a universe like the one we observe. One can show this by considering a very different state for the universe at the present time, say a very lumpy and irregular one. One could use the laws of science to evolve the universe back in time to determine its configuration at earlier times. According to the singularity theorems of classical general relativity, there would still have been a Big Bang singularity. If you evolve such a universe forward in time according to the laws of science, you will end up with the lumpy and irregular state you started with. Thus, there must have been initial configurations that would not have given rise to a universe like the one we see today. So even the inflationary model does not tell us why the initial configuration was not such as to produce something very different from what we observe. Must we turn to the Anthropic Principle for an explanation? Was it all just a lucky chance? That would seem a counsel of despair, a negation of all our hopes of understanding the underlying orders of the universe. In order to predict how the universe should have started off, one needs laws that had at the beginning of time. If the classical theory of general relativity was correct, the singularity theorems that Roger Penrose and I proved showed that the beginning of time would have been a point of infinite density, an infinite curvature of space-time. All the known laws of science would have break down at such a point. One might suppose that there were new laws that held at singularities, but it would be very difficult even to formulate such laws at such badly behaved points, and we would have no guide from the observations as to what those laws might be. However, what the singularity theorems really indicate is that the gravitational field becomes so strong that quantum gravitational effects become important. Classical theory is no longer a good description of the universe, so one has to use a quantum theory of gravity to discuss the very early stages of the universe. As we shall see, it is possible in the quantum theory for the ordinary laws of science to hold everywhere, including at the beginning of time. It is not necessary to postulate new laws for singularities, because there need not be any singularities in the quantum theory. We don't yet have a complete and consistent theory that combines quantum mechanics and gravity. However, we are fairly certain of some features that such a unified theory should have. One is that it should incorporate Feynman's proposal to formulate quantum theory in terms of a sum of over histories. In this approach, a particle does not have just a single history, as it would in a classical. Instead, it is supposed to follow every possible path in space-time, and with each of these histories there are associated a couple of numbers, one representing the size of the wave and the other representing its position in the cycle, its phase, the probability that the particle, say, passes through one particular point is found by adding up the waves associated with every possible history that passes through that point. When one actually tries to perform these sums, however, one runs into severe technical problems. The only way around these is the following peculiar prescription. One must add up the waves for particle histories that are not in the real time that you and I experience, but takes place in what is called imaginary time. Imaginary time may seem sound science fiction, but it is in fact a well-defined mathematical concept. If we take any ordinary or real number and multiply it by itself, the result is a positive number. For example, 2 times 2 is 4. But so is negative 2 times negative 2. There are, however, special numbers called imaginary that give negative numbers when multiplied by themselves. The one called iota, when multiplied by itself, gives negative 1. 2 iota multiplied by itself gives negative 4, and so on. To avoid the technical difficulties with Feynman's sums over histories, one must use imaginary time. That is to say, for the purposes of the calculation, one must measure time using imaginary numbers rather than real numbers. This has an interesting effect on space-time. The distinction between time and space disappears completely. A space-time in which events happen, imaginary values of time coordinates, is said to be Euclidean, after the ancient Greek Euclid, who founded the study of geometry of two-dimensional surfaces. What we now call Euclidean spacetime is very similar, except that is, it has 4 dimensions instead of 2. In Euclidean spacetime, there is no difference between the time direction and directions in space. On the other hand, in real space-time, in which events are labeled by ordinary, real values of the time coordinates, it is easy to tell the differences. The time directions all points lies within the light code, and space directions lie outside. In any case, as far as everyday quantum mechanics is concerned, we may regard our use of imaginary time and Euclidean spacetime as merely a mathematical device or trick to calculate answers about real space-time. A second feature that we believe must be part of any ultimate theory in Einstein's idea that the gravitational fields is represented by curved space-time particles try to follow the nearest thing to a straight path in a curved space. But because space-time is not flat, their paths appear to be bent, as if by a gravitational field. When we apply Feynman's sum-over histories to Einstein's view of gravity, the analog of the history of a particle is now a complete curved spacetime that represents the history of the whole universe. To avoid the technical difficulties in actually performing the sum-over histories, these curved spacetime must be taken to be Euclideans. That is, time is imaginary and is indistinguishable from directions in space. To calculate the probability of finding a real space-time with some certain property, such as looking the same at every point and in every direction, one adds up the waves associated with all the histories that have that property. In the classical theory of general relativity, there are many different possible curved spacetimes, each corresponding to a different initial state of the universe. If we knew the initial state of our universe, we would now know its entire history. Similarly, in the quantum theory of gravity, there are many different possible quantum states of the universe. Again, if we knew how the Euclidean curved spacetime in the sum-over histories behaved at early times, we would know the quantum state of the universe. In the classical theory of gravity, which is based on real space-time, there are only 2 possible ways the universe can behave. Either it has existed from an infinite time, or else it had a beginning at a singularity at some finite time in the past. In the quantum theory of gravity, on the other hand, a third possibility arises, because one is using Euclidean spacetimes, in which the time direction is on the same footing as directions in space. It is possible for space-time to be finite in extent and yet to have no singularities that formed a boundary or edge. Space-time would be like the surface of the Earth, only with 2 more dimensions. The surface of Earth is finite in extent, but it doesn't have a boundary or edge. If you sail off into the sunset, you don't fall the edge or run into a singularity. I know, because I have been round the world. If Euclidean spacetime stretches back to infinite imaginary time, or else starts at a singularity in imaginary time, we have the same problem as in the classical theory of specifying the initial states of the universe. God may know how the universe began, but we cannot give any particular reason for thinking it began one way rather than another. On the other hand, the quantum theory of gravity has opened up a new possibility in which there would be no boundary to space-time, and so there would be no need to specify the behavior at the boundary. There would be no singularity at which the laws of science broke down, and no edge of space-time at which one would have to appeal to God or some new law to set the boundary conditions for space-time. One could say the boundary conditions of the universe is that it has no boundary. The universe would be completely self-contained and not affected by anything outside itself. It would neither be created nor destroyed. It would just be. It was at the conference in the Vatican mentioned earlier that I first put forward the suggestion that maybe time and space together formed a surface that was finite in size but did not have any boundary or edge. My paper was rather mathematical, however, so its implications for the role of God in the creation of the universe were not generally recognized at the time. Just as well for me. At the time of the Vatican Conference, I did not know how to use the no boundary idea to make predictions about the universe. However, I spent the following summer at the University of California, Santa Barbara. There, a friend and colleague of mine, Jim Hartle, worked out with me what conditions the universe must satisfy if space-time had no boundary. When I returned to Cambridge, I continued this work with two of my research students, Julian Larrell and Jonathan Halliwell. I would like to emphasize that this idea that time and space should be finite without boundary is just a proposal. It cannot be deduced from some other principle, like any other scientific theory. It may initially be put forward for aesthetic or metaphysical reasons, but the real test is whether it makes predictions that agree with observations. This, however, is difficult to determine in case of quantum gravity for two reasons. First, as will be explained in the next chapter, we are not yet sure exactly which theory successfully combines general relativity and quantum mechanics, though we know quite a lot about the form such a theory must have. Second, any model that described the whole universe in detail would be much too complicated mathematically for us to be able to calculate exact predictions. One therefore has to make simplifications and simplifying assumptions and approximations. And even then, the problem of extracting predictions remains a formidable one. Each history in the sum of our histories would describe not only the space-time, but everything in it as well, including any complicated organisms like human beings who can observe the history of the universe. This may provide another justification for the Anthropic Principle, for if all the histories are possible, then so long as we exist in one of the histories, we may use the Anthropic Principle to explain why the universe is found to be the way it is. Exactly what meaning can be attached to the other histories, in which we do not exist, is not clear. This view of a quantum theory of gravity would be much more satisfactory. However, if one could show that using the sum of our histories, our universe is not just one of the possible histories, but one of the most probable one. To do this, we must perform some of our histories for all possible Euclidean space-time that have no boundary. Under the no-boundary proposal, one learns that the chance of the universe being found to be following most of the possible histories is negligible. But there is a particular family of histories that are much more probable than the others. These histories may be pictured as being like the surface of the Earth, with the distance from North Pole representing imaginary time and size of the circle of constant distance from the North Pole representing the spatial size of the universe. The universe starts at the North Pole as a single point. As one moves south, the circles of the latitude at constant distance from the North Pole get bigger, corresponding to the universe expanding with imaginary time. The universe would reach a maximum size at the equator and would contract with increasing imaginary time to a single point at the South Pole. Even though the universe would have zero size at the North and South Poles, these points would not be singularities, any more than the North and South Pole on the Earth are singular. The laws of science will hold at them. just as they do at the North and South poles on the Earth. The history of the universe in real time, however, would look very different. At about 10 or 20,000 million years ago, it would have a minimum size, which was equal to the maximum radius of the history in imaginary time. At later real times, the universe would expand like the chaotic inflationary model proposed by Lindy. But one would not now have to assume that the universe was created somehow in the right sort of state. The universe would expand to a very large size and eventually it would collapse again into what looks like a singularity in real time. Thus, in a sense, we are still all doomed, even if we keep away from black holes. Only if we could picture the universe in terms of imaginary time would there be no singularities. If the universe really is in such a quantum state, there would be no singularities in the history of the universe in imaginary time. It might seem, therefore, that my more recent work had completely undone the results of my earlier work on singularities. But as indicated above, the real importance of the singularity theorems was that they showed that the gravitational field must become so strong that quantum gravitational effect could not be ignored. This in turn led to the idea that universe could be finite in imaginary time, but without boundaries or singularities. When one goes back to the real time in which we live, however, there will still appear to be singularities. The poor astronaut who falls into a black hole will still come to a sticky end. Only if he lived in imaginary time would he encounter no singularity. This might suggest that so-called imaginary time is really the real time, and that what we call the real time is just a figment of our imaginations. In real time, the universe has a beginning and an end at singularities that form a boundary to space-time and at which the laws of science break down. But in imaginary time, there are no singularities or boundaries. So maybe what we call imaginary time is really more basic, and what we call the real is just an idea that we invent to help us describe what we think the universe is like. But according to the approach I described in Chapter 1, a scientific theory is just a mathematical model we make to describe our observations. It exists only in our mind, so it is meaningless to ask which is real or imaginary time. It is simply a matter of which is the most useful description. One can also use the sum over histories along with the no-boundary proposal to find which properties of the universe are likely to occur together. For example, one can calculate the probability that the universe is expanding at nearly the same rate in all different directions at a time when the densities of the universe has its present value. In the simplified model that have been examined so far, this probability turns out to be high. That is, the proposed no-boundary condition leads to the prediction that it is extremely probable that the present rate of expansion of the universe is almost the same in each direction. This is consistent with the observations of the microwave background radiation, which show that it has almost exactly the same intensity in any directions. If the universe were expanding faster in some directions than in others, the intensity of the radiation in those directions would be reduced by an additional redshift. Further predictions of the no-boundary conditions are currently being worked out. A particularly interesting problem is the size of the small departures from uniform density in the early universe that caused the formation first of the galaxies, then of stars, and finally of us. The uncertainty principle implies that the early universe cannot have been completely uniform because there must have been some uncertainties or fluctuations in the position and velocities of the particles. Using the no-boundary condition, we find that the universe must, in fact, have started off with just the minimum possible non-uniformity allowed by the uncertainty principle. The universe would have then undergone a period of rapid expansion, as in the inflationary models. During this period, the initial non-uniformities would have been amplified until they were big enough to explain the origin of the structure we observe around us. In an expanding universe in which the density of matter varied slightly from place to place, gravity would have caused the denser region to slow down their expansion and start contracting. This would lead to the formation of galaxies, stars, and eventually even insignificant creatures like ourselves. Thus, all the complicated structures that we see in the universe might be explained by the no-boundary conditions for the universe together with the uncertainty principle of quantum mechanics. The idea that space and time may form a closed surface without boundary also has profound implications for the role of God in the affairs of the universe. With the success of scientific theories in describing events, most people have come to believe that God allows the universe to evolve according to a set of laws and does not intervene in the universe to break these laws. However, the laws do not tell us what the universe should have looked like when it started. It would still be up to God to wind up the clockwork and choose how to start it off. So long as the universe had a beginning, we could suppose it had a creator. But if the universe is really completely self-contained, having no boundary or edge, it would have neither beginning nor end. It would simply be what place then for a creator. See you in the next chapter. Till then, take care. Bye-bye. Have a great day. Thank you very much for watching. If you want some more videos like this one, please like, share and subscribe to my channel. Have a great day. Stay home. Stay safe.